Welcome to today's webinar with the title Experience the Flexibility Part 2 Physical PCB Sample WE.flextwo. I am Andreas Schilp, your host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speaker in today's webinar is a qualified specialist from Würth Elektronik, Klaus Schilmulak from our Technical Project Management. Welcome back, Klaus. And now I wish you lots of fun and new information.
Thank you very much, Andreas, and good morning. Today we want to talk about rigid flex with flex on the inner layers. One of the last webinars deals with the flex on the outer layers. I hope you watched it. So this is the second presentation of flex technology offered by Würth Elektronik. And there will be another webinar in November who is dealing with flex technology. So first of all, before we start, let me shortly introduce myself. My name is Klaus Schilmulak, and as Andreas told, I'm working in the technical project management at Würth Elektronik. So first question is, of course, what is the technical project management? In this department, we deal with special customer requirements apart from the standard you will find in the design rules or design guides. And we will also look on the realization of the products in the process flow in production itself. So if you have any questions about rigid flex PCB, dealing with other things like different materials, other technologies like inlays or HDI, just contact us and we will be happy to help you. We are five persons working in this team, just looking on customer requirements and solutions. In today's webinar, we will talk about, of course, the PCB sample itself, the materials, the stackups. We will talk about signal integrity and this technology with inner layer flex. We will talk about SIF contacts and lift-off areas. And of course, at last, we will talk about design rules and some specific requirements in this case. So here's again, in this picture, you can see first point is, of course, material in the flex area, material in the rigid area. Here you see the SIF connector. We have the lift-off area here. And we will talk about special requirements, as I told already, in the design rules, dealing with the area, the flex rigid transition area here, and drillings in PTH and the overlap of the cover lay. So that's what we will talk about today. If you have any questions, just set it in the chat, or you can ask afterwards, of course. So the first point, what I want to talk about is the material in the flex area and the material in the rigid area, which Würth Elektronik use for the build-up of rigid flex boards. In the rigid area, we use material according to IPC 4101, 127, 128. This is material with a TG of 150, 170, and it's an FR4 material. So that's the main material we use for this PCB. And you will find this in our standard stack-up as well, especially the 150 TG. For the rigid part, apart from the FR4 material, we can offer a PPE material, which is for high frequency or high speed build-ups, and we can offer a high reliability material with polyamide glass, with a TG up to 240. So this is really high reliable material, which we can use for rigid flex boards. In the flexed area, especially for the polyamide laminate, we use only adhesive-free laminate in accordance to IPC 4202-11. So the reason for that is, again, reliability. If we use polyamide laminate with adhesive between the polyamide and the copper, this adhesive has a high expansion in the z-axis. So this is a real problem for reliability, and that's the reason why we only use adhesive-free laminates. For the coverlay, on the flex part and in the overlap to the rigid part, we use material looking on IPC 4203 1 and JPC DG04. And we use the material only in the flexible area and a small zone of overlap in the rigid transition. Reason for that is, again, reliability. So the cover layer will always be far away from the next drilling. That's the main point for reliability. So we will never find a cover layer going in the rigid part and into the drilling areas or the PTHs. There you can see the process flow of a rigid flex board with an inner layer flex. Here in this example, it's a 2F in the middle here. Yeah, the flex layer. The flex layer is you can see it in the diagram. It's right here. Yeah, it's the flex material, the etching part, and the cover lay, which is bonded or laminate to the flex area here. Yeah, so we have to cut the cover lay. We do this by laser or by a cutting tool, and we have to fix it on the flex and on the polyamide on the flex in the flex area. On the other side, we have to cut the to route the pre-pregs. Yeah? We have to do this for the cover for the cover. You have to do it for the pre-preg, sorry, and for a spacer used in the flex area to prevent resin flow. What you see here, the white colored, it's a standard multi-layer process for rigid materials. Okay, you have to use this as well in the rigid flex boards. These are these two cores here on the upside and downside. So all these materials come together, I would say, before multi-layer, yeah, before the lamination step, and after the lamination step, I would say everything runs in the same way as it used for a rigid multi-layer. The only exception is the depth milling at the end to remove the rigid parts here in the flex area. Yeah. So the most work or the main work for rigid flex boards is in the beginning before lamination of the board. So next step is I want to talk about signal integrity in the flex part and in the rigid part. Here you can see an example. Yeah, it's a USB camera. And you see there, of course, we need impedance-defined signals. There's an USB connector at the end here, connecting in the rigid area. And of course, there's no place for any connectors. Less footprint area, of course. And with a rigid flex board, we can have the solution for that. And of course, I would say in one of the first steps of the layout, we have to look on impedance. Yeah. So what we can do is a calculation of impedance. We can do a documentation of impedance. We can do that for the rigid part, for the flex part, and we can match it, I would say. The best way is to come to us quite early, and we can check everything, looking on the material as well as on the line-spaced structures. That's what we can do in the beginning of a layout, and of course even if it's finished, but maybe you have to do some changes. So one point is here, as you can see, we have high, it's very important, or good high influence on the impedance values is a hedge in the flex area. This means we open the copper on the reference layer. Yeah, you can see it here beneath the traces. Yeah, this has two main effects. We can have a variation of the impedance. We can deal with impedance values. We improve the flexibility of the flex part, of course, if we open the copper. We have better drying effects on the flex material, so we can better get off, of course, humidity if we have less copper. And of course, we can increase the impedance values. It's the same as we can change material. Yeah, if you look here, you have different polyamide foils. Polyamide foils are available from 25 up to 125. Standard thickness is 50 micron. I would say this is the standard price. Everything, if it's thicker or thinner, increase the price. So, but we can deal with it, looking on impedance values, as well as we can do this with the hedge, yeah? And left copper on the flex part, which we have after this hedging. So a big influence, yeah, on impedance, what we can do. And of course, another solution is, or a compromise for that is, we have full copper beneath the differential pair of conductors here. Yeah, we use full copper and open the area between the traces and make a hedge. Yeah, so you have better drying, better flexibility, but you still have the impedance values if it's needed with full copper. Another point on the sample is the SIF connectors and the lift-off area. Andreas, maybe you can open the camera.
Just a second. Camera speaker. So here we are.
Okay, thank you very much. So there you see the SIF connector here, yeah, and you see the lift-off area. I will do it here. You can see it, yeah, and you see. I just left it here. It's a tab, yeah, to fix this lift-off area. It's also here, right in the flex part, but I opened it already. So we have some tabs in the flex area which fix this lift-off area here, yeah, and the SIF connector itself, it's laser cut and it's fixed itself because there's no tab here, but it's fixed, yeah. So that's what we talk about now. Thank you very much, Andreas. In general, it's the same procedure as we do this for if we have the flex on the outer layer. We recommend strictly to avoid the flex, the SIF connector on the inner layer areas. Yeah. So what we do is we want we say put this flex part on the outer layer, yeah, using drills, yeah, because of production issues, what I want to explain later. Yeah. So we want to show you, I would say, the alternative for an inner layer SIF connector, and we want to transfer it to the outer layer. So in the picture on the right corner, you see the SIF connector, you see the flex part here coming here, running in the middle of this rigid part, and you see the SIF connector itself, it's on the outer layer. Yeah, so we transfer it here by using through holes, yeah, to the outer layer, Yeah? That's the flex inner layer here, it's the inner layer, and that's the outer layer. And the SIF connector is on the outer layer. So what we do is we do a depth milling here. Yeah. So we have the thickness, to define thickness of the SIF connector. Then we do a laser cut, and so we can put it out on, or lift it off, I would say. And if we have here, you can see it on the left side. We have the lift off area. We can take the SIF connector and lift it up to the next rigid part here. Okay. The reason for our I would say for this solution is creating the SIF connector on the inner layer will show some problem in production. During the layup, if you remember the stack up, we have pre-breaks, and pre-break is brittle and rigid, is brittle in this status in the lamination, before lamination. So we have dust. And during the layup, it is possible that we get some pre-break dust on the connector fingers, right here. So we have pre-break dust or resin spots after lamination on the copper, and of course, if we have it on the copper, we can't remove it. We have it on the gold fingers as well. Yeah. So if you can shift the connector from the inner layer to the outer layer by using these plated through holes, we don't have this problem. And of course, we have nearly a standard process. We do this depth milling in creating the end in the final department of the contour routing in the same step. So that's not I would say not an additional process. If you have the gold fingers on the inner layer, it's a quite, I would say, let me say, complex process which we have to run in production. So the laser itself, the laser tool here, the registration on the conductor patterns here, so it fits very tight to all the outer layers. So typical PCB relevant drawings on SIF contacts is the definition of the contour itself and all the tolerances. Yeah, it's here, or the tolerances in the thickness. Yeah. And then you can say the smaller the pitch, the smaller is the tolerance of the structures. Thickness tolerance itself, you can see it here, is 0.05 millimeters or 50 micron typically. You can always also find SIF connectors with 30 micron thickness tolerance. The standard tolerance is 50 micron, and for that we use a depth milling, a routing process, which is also used for removing the rigid parts. So it's a standard process, and I would say we do it in one run. Yeah. If we have thinner thickness, we have to change from FR4 and depth milling to a polyimide reinforcement. For the contour tolerance, we always have to use a laser cut. Yeah. Reason of that is really tight tolerances, and especially tolerance finger contacts to contour, yeah, or small radii for the interlocks. Yeah. That's the main reason why we use a laser cut, or we always use laser cut for creating the contour. So there's some pictures of these two solutions. On the left side, you see the FR4 stiffener. You see here the laser cut of the SIF connector itself. Of course, the laser cut goes in the flex area as well. Yeah. That's a picture looking from the back side. You see the depth milling area here. You see I would say this black line is the transition line between this stiffened area and the flex area here. Yeah? And you can, I would say, maybe imagine the laser cut running through to the flex area on both sides. Yeah? So, and if you lift the connector, you see here the connector area and the lift off area, which is also laser cutted. On the other hand, on the right side, you see a polyamide stiffener, which we have to use if we have a specification of 30 microns tolerance. Therefore, we need, I would say, a lot of additional production steps. We have to cut the polyamide foil. We have to insert the polyamide. That's a manual step. So we have increasing cost, of course, for this solution, but it's possible. But depending on the size of the polyamide stiffer itself, which could be very small, we have to check manufacturability. Sometimes you find solution, but if it's too small, it's nearly impossible to realize the solution. So we always have to look on the manufacturability of these boards, if it's possible or not. Yeah, it's always possible with an FO4, but polyamide have some restrictions. So in this part of the webinar, I would like to discuss the topic of design rules for rigid flexed PCB. And maybe you have experience with this in the past. The most frequent point for queries or clarification is the distance between plated through holes in the rigid area and the flex transition zone here. Yeah. As you see in this graphic, we have you see the polyamide laminate here, yeah, with copper, of course, and you see the cover lay on top, on top and on bottom of the flex part, and you see an overlap of the cover lay into the rigid area. So now we can say, okay, that's Würth Elektronik, but it's not only Würth Elektronik, and of course we work always looking on the IPC, if it's for design or manufacturability, or if it's for any testings or checks, quality checks. Always IPC is in the back. Yeah, and so if you look on the design rules for rigid flex boards, which is described in the 2223 IPC. This design rule explicitly refers to the rigid flexible transition area. Yeah? So there's a definition of a distance between plated through holes, which is next to the transition area, and the transition area itself. Yeah. So here it is, as you can read, the distance plated through hole is it's more than 3 millimeters. Yeah. And we have to calculate the diameter of the tool size as well. So I would say roughly it's 3.5 millimeters. It's the distance from the through hole to the rigid transition area. And there's a definition of a cover lay overlap, yeah, which I showed you before in the graph, which is defined 1.27 or up to 2.5 millimeters in the rigid part. So, and if you look on these two values, you will see we have this maximum overlap of 2.5 millimeters, and we have a definition of distance plated through hole in minimum, I would say, let me say 3.2 millimeters. So there's a different 700 microns distance cover lay maximum overlap to the plated through hole in general. Yeah. So that's the first part of definition. The next definition is the IPC 6013, which always shows some details of the rigid flex transition area. In particular, it deals with deviations and imperfections. That's normally nothing what we want to talk about, want to hear, of course. If you look here on the right picture, you see here in this red angle area, that's what you want to have it, and that's what, of course, Würth Elektronik want to have in a perfect form. Yeah. The gray material is the pre-preg. Yeah? You have the cores, you have copper. Everything is fine. There's a defined, I would say, contour, and we have the flex part here, the rigid part here. Everything is fine. It's perfect. But of course, we deal with resin, and resin must flow. Yeah, it's definitely needed. So of course, we tried that we find a stop for this resin flow in the resin area and in the rigid in the flex area, but it's not possible always. So we have a resin flow into the flex area, or we have a restricted flow. This means, I would say, we have some kind of opens, yeah, or not opens. We're missing material here, yeah. There's no flow of the resin right to the end of the contour. So this could happen as well, yeah. Or in the bad picture here, you see we have missing material. We have missing material on the flex part, and we have missing material in the rigid part, yeah. So this is definitely the wrongest picture, yeah. So there's no overlap of the cover layer of the pre-preg on the copper. There's no filling, yeah. So missing isolation in the inner layer and missing isolation here on the copper next to the flex part. That's definitely the way it should not be, yeah. But it's defined in the IPC. It's possible, and this area is defined in the IPC as well. 1.5 millimeter into the rigid part, 1.5 millimeter here in the flex area. Yeah? So we can have a non-laminated area. Yeah? We can have adhesive squeeze out. We can have deviation in the thickness of the pre-preg here. Yeah, as well. Yeah. And the IPC have a recommendation for the cover lay for the overlap, which is minimum 0.6 millimeter. Yeah. So remember the design IPC, which is talking about 3 plated through hole, minimum 3.2 millimeters far away from the flex part, and overlap of the cover lay to maximum 2.7 millimeters. So here the recommendation is 0.6 millimeters. So what is Würth Elektronik working on this? We define the symbol or value G in our design rules. Yeah, that's what you can find here on the right side. Yeah, and here's a diagram as well, a graph. We have calculated and tested everything, of course, and we define values. This means PET to flex transition zone, the flex transition in minimum 0.5 millimeters, or if we have advanced and we have checked layout and we have checked copper distribution, we can reduce it down to 1 millimeter. That's for if we have a stack up with 2-layer flex. If we have more flex layers, we have to increase these values. Yeah. So in standard, we have then 2 millimeters, and we can reduce it to 1.5 millimeters. But I think, I hope you understand the reason for this restriction. And we have a lot of questions and discussion with customers why we need this distance and why they have to shift drillings. This is just because of technical restrictions, yeah, and IPC standards, which need a minimum overlap, and that's what we have, of course, in our PCB and in our manufacturing as well. We define here an overlap of the cover layer, and this is defined 0.6 millimeter minimum, yeah, and that's the reason for the values we define here in our design rules. So I think you can understand that, the reason for that, and I'll look back on the design rules as well, and why you can find, of course, this in our new samples of 2F, because of a lot of questions concerning on the distance of the plated through holes to the flex part. So thank you very much for your attention here now for this webinar. Of course, you can always contact us if you have any questions, even in an early layout stadium. Just ask us for impedance. We can calculate you the values. Just ask us, come to us. We will be happy to have to contact you. Thank you very much.
Okay, thank you very much, Klaus, for the detailed explanation about the RIGID.flex technology and the new physical PCB sample. So, I'd like to show our website. Here you can find even another detailed description about the physical PCB sample. We can see different pictures, details, of course, slot and key, mechatronical design, again details about the outline, QR code, and so on and so on. So here you can find a lot of additional information about the PCB sample. And last but not least, you can also order your personal physical PCB sample here. Just fill in your data and then we are pleased to send the samples to you.